Recording will begin soon. Yeah, the recording has begun. So before vacation, we came to know what do we mean by center of mass frame and the left frame, and we saw the how we can study or analyze a perfectly elastic collision in both the frames. Okay, so today we will investigate another case of collision, that is the inelastic collision. Can anyone tell me what do you mean by inelastic collision? How far you remember from the classes before vacation? Let's see. Anyone? You can take help from your previous class notes. You can just recapture it. What do you mean by inelastic collision? Yes, Neha, Latung, anyone?
Sir, in inelastic collision, no, the particles before and after the collision will be same.
Yeah, okay. And is there some difference in anything before and after the collision?
Uh, so it's like kinetic energy, like maybe gain or loss.
Okay, that is there is a change in energy. Energy is
Yeah.
either gained or lost, right?
Loss.
That's correct. Okay, so those cases are more practical. Okay, they are more visible. So let us try to study one such case. Let us take the one-dimensional case for simplicity. Let us again begin with the lap frame. That is, you are a spectator. You are sitting on a chair and you're looking into the situation as if you are watching it on a television. So what are you seeing? You are seeing, suppose, again, two particles, one of mass m1 is moving with u1 velocity, another one of mass m2 moves with a velocity u2. Okay, and we are assuming that say the velocity u1 is more than velocity u2. And what happens after collision? This is before collision. What happens to them after collision? Say they become one single system and it moves with a velocity, say, v. Okay, as if they got stuck together. Now they are moving with a velocity, say, v. So let us try to write the conservation principle uh, equations, or let us update that. So for conservation of linear momentum, what we can say? We can say that total linear momentum before collision is equal to total linear momentum after collision. So before collision, what we can write? I'm dropping off the vector signs. Okay, just I'm looking into the magnitude. So that is the sum of individual linear momenta before collision. After collision, what we have? We have one system. I mean, that is one mass we can consider is moving with a velocity v. So we can write the expression for that. You can say it is kind of common velocity. The velocity is v. So that is the expression of the velocity with which the system is moving after collision. So now we can have some special cases like, say, if one of them were at rest initially, what happens? Suppose this one was at rest initially. Then you can write this thing. So the final velocity would look like this. Okay. Just you may get this kind of thing in the exam for a short answer type question, that uh, write the expression for the final velocity in case of one-dimensional elastic collision when one of the two particles is initially at rest. Okay. Now let us check the loss. Okay. So what is the loss in kinetic energy? That is what Neha said, that there can be either a loss or gain in the kinetic energy. Okay. Suppose we are analyzing the loss. So before collision, uh, let me make you aware of one thing, that in physics, in different branches of physics, same thing is denoted by different letters. Like a kinetic energy uh, is denoted sometimes with the letter capital T. Okay. In our school days, we were accustomed to use this thing. We could write like this K dot E. Okay. But in higher physics, in many branches, you will find kinetic energy is denoted by capital T. Potential energy is sometimes denoted by capital V or capital U. Okay. Anyways, so here I'm denoting it by capital letter T. I'm calling that kinetic energy before collision as P1. So what was it? It was simply sum of the individual kinetic energies. As simple as that. What happened to the kinetic energy after collision? Say it's T2. So after collision, we are considering only one mass, as if there is only one mass, m1 plus m2. This thing. So therefore, what is the loss? Loss in kinetic energy. I'm denoting it by the letter delta T. Again, delta, this thing is denoted, it tells us about gain, loss, or difference. Okay, so simply it is T1 minus T2. Why? Why not T2 minus T1? If it is T2 minus T1, that means the energy after collision is more than energy before collision. That means T2 minus T1 will represent the gain, and T1 minus T2 is representing the loss. Okay. So let us put the values. So now we will be recording to substitute the value of V in terms of U1 and U2, because you can see uh, here we already have U1 and U2. We have another parameter V. So let's try not to complicate things. So we can substitute this value of V in the expression that we just got. So what is delta T? The first two terms would remain unchanged. M1 plus M2 has nothing much to do. What about V? V is now, if we substitute, it's actually V square. This. I can see this term is repeating twice, so I can cancel one term. Then uh, I can take the LCM. Okay. Before that, I want to break this whole square term. Don't hurry and don't panic. It's not nothing difficult at all. Just follow the steps. Uh, Proceed gradually. So a square plus b square plus 2ab. You would have done the LCM, then you would have broken this up. But my personal experience says that that step is more complicated because you have to multiply so many things and you may end up making some errors. Okay, it's up to you. If you're feeling comfortable with that, no problem. So now I can take the LCM. So let's begin with multiplying m1 with these two terms. That would give me m1 square u1 square plus m1 m2 u2 square. Now the term for m2, m1 m2 u1 square m2 u2 square minus, I think I'll get short on space. I'll write it in small fonts, m1 m2 u1 u2. Sorry, I think this is m1 square. Yeah, square. Is it okay with both of you? Fine. I can see m1 square and u2 square getting cancelled. This thing is not, I mean, it's pretty uncomfortable to put a long dash and write it. So better I can write the thing like this so that it looks a bit compact and less clumsy. Now I will write the remaining terms. What is left behind? Let's see. Mm, I have m1, m2, u2 square, m1, m2, u1 square. Mm, I think I made a mistake here. It would also be this thing. Oh, then this thing will also get cancelled out. Please check it yourself once. That is what I was talking about. This multiplication things are a bit complicated at times. Anyways, I'm getting this thing. So you can see m1 m2 is present in all the terms. Take it common. That would give me u1 square u2 square minus 2 u1 u2. A square plus b square minus 2ab. Now the question is that how to write it. Whether I would write it like this or like this. You can see the expansion is same. These two are equal, isn't it? A square plus b square minus 2ab, b square plus a square minus 2ba. Same thing. But keep in mind, what we said initially, u1 was greater than u2. So it is always wise to express the thing like greater minus smaller, like this m1 m2. Okay, this thing, not u2 minus u1 whole square. However, u2 minus u1 whole square won't do any harm in this case because it's a whole square. In fact, at the end of the day, when you square any negative quantity, it would be positive. Okay, but in some other cases, these things may give you some peculiar result. Anyways, you can see m1, m2, these all are positive quantities, isn't it? So this entire thing is always positive. Here you have a whole square thing, and the thing inside is not an imaginary quantity; it's a real quantity. So overall, I can say this entire thing is always greater than 0. Okay, that means there is always a loss in kinetic energy in this case. Had this thing been less than 0, then what it would have implied? It would have implied that energy after collision is more than energy before collision, because we are doing energy before collision minus energy after collision. Okay, so we can confirm that there is a loss in kinetic energy. Now again, if we take that special case when the second body was at rest initially, then we can get some simplified result. Then we can say the loss in kinetic energy is equal to simply this. Just put u2 equal to 0 in this expression, then you will get this. That is a special case when one of the bodies, two bodies were initially at rest. Is it clear, both of you? Any doubt? Okay, fine. So now let us see how the situation looks like in the center of mass frame, isn't it? We know about that frame. So nothing, no doubt. Then let's move on. So what happens to this thing in the center of mass frame, or in the C frame in short? So as we discussed in the last class, that we have to consider the velocity of the center of mass. So what is that? Velocity of the center of mass is, say, v cm, denoting it like this. Okay. So let me say that the velocities in the C frame, let me call them u1 dashed and u2 dashed respectively. So we can now apply the Gaussian transformation equations, isn't it? Why we require that? That also we discussed that uh, at the end of the day we are taking the readings in the left frame only, isn't it? It's not possible for us to sit in the center of mass of the two bodies and constantly monitor everything. But if we imagine it that way, our analysis would be simple. So having done that, to make the imagination into reality, we have to express everything in terms of the data of the left frame. For that, we need to express what phenomena happened in the C frame in terms of the L frame. For that, we can use the Gaussian transformation, provided that the center of mass frame is an inertial frame. And we also saw that it is an inertial frame where dv dt was equal to 0, isn't it? Rate of change of total momentum was 0. That means total momentum can be written as the total momentum of the system can be written as total mass with the velocity of the center of mass. And if this is 0, if this thing is 0, that means ddt of this thing is also 0. That means we can say that center of mass is velocity of the center of mass is constant. That means the C frame is a uniform frame. Sorry, inertial frame. Easily we can write the Gaussian transformation equations due to this thing. Okay. Because many people blindly just note down the steps, but you have to understand it. Because in physics, most of the time we are overwhelmed with the calculations, the mathematical part, but that is not everything. That is just a small fraction. Okay. Uh, I'm keeping it like this. I'm not doing the LCM. There's a reason behind that. And what about the another velocity? It would look like this. I can feel that everyone, both of you want to quickly do the LCM. I'm not doing it because what happens if one of the two bodies were initially at rest in the left frame? Okay. You may ask that, sir, why are we taking this thing? I mean, why are we always, sorry, so much worried about the case when one of the bodies is at rest and the another one is moving? The reason is that when you will study nuclear physics, particle physics, or atomic physics, there are cases when we have a target which is at rest. It is bombarded with high energetic particles. Okay, like you can have a target of molybdenum and you are hitting it with high energetic, say, X-rays. That is also a case of collision, isn't it? So uh, this thing, this situation is very much uh, practical in experimental physics. Okay, that's why we are studying this thing. Okay, don't be under the impression that if we are making one, if we are doing this thing, then the equation will be it's simplified. That is the consequence, but that is not the rationale behind considering this thing. Okay, because in collision, many times we will have a target which is at rest, and we are hitting it by another, bombarding it with an energetic particle. So what happens if this thing occurs? Then you can see here this term would become 0. I can LCM, do the LCM, or I can write it like this as well. No problem, I can do the same also. It will give me something like this. So you can see this velocity is proportional to the corresponding velocity in the L frame. And what happens to u2 dash? This term would be 0, this would be 0. So I'll be having only this thing. So definitely it is proportional to the velocity, corresponding velocity in the L frame, but you can see the direction has changed. Okay. That is the situation in the C frame. Last day also we saw that we took that example of a car moving towards a tree, and you're watching from here. And if you think of the center of mass, suppose it is somewhere here, then you're standing here. What you will see as time progresses, the car is moving closer to the tree, and as this length decreases, what will happen? The center of mass will also be changing. And if you are at the center of mass, you will just feel that slowly both the things are coming towards you. And since they're coming towards you, that means that the velocities would be in opposite direction. That is where the negative sign has come here. Is it clear? Please respond if you have any doubt, if you want to comment anything about this. So that's good. We can proceed. Now, another important quantity we have to study when it comes to collision. This quantity automatically follows. You read little bit about this in your 11th standard, I guess. That is something called coefficient of restitution. Okay, do you remember anything from this topic? Anything that you remember? Did something strike you in your mind when you heard this thing? Okay, maybe you don't remember. It's okay. Actually, this quantity was not given that much importance. Unfortunately, the situation will be like this in your honors course as well, but in real life it is very important. Okay, uh, so what we saw that for a perfectly elastic collision, okay, in the one-dimensional case, we got this result that the velocity of separation was equal to the velocity of approach, meaning that the velocity with which both the bodies were heading towards each other before collision is equal to the velocity with which both the bodies are moving away from each other after the collision. Okay, let me write that result for you. You may recollect it then. It was something like this. I'm putting in a third bracket. It was something like this. Okay, the minus sign is indicating that uh, if this is the velocity of separation, this would be the velocity of, sorry, if this is the velocity of approach, it is the velocity of separation. Isn't it? We got this result. This is for perfectly elastic collision. And today what we studied is actually a perfectly inelastic collision. Okay. So for a perfectly inelastic collision, what we made, what picture did we draw? That after the collision, both the bodies are, they stuck together as if they were glued together and they are moving as a one single body. So can you tell me what is the velocity of separation in this case? What is the velocity of separation in case of a perfectly inelastic collision? Anyone? What do you think it would be? I mean, in terms of number. 1, 2, 3, 4, 5, 6, 0, 9, 10, 20, minus 1. What do you think? Yeah, very good. Yeah, it would be 0. They are not separated at all, isn't it? They are not together. Before collision, they were moving like this. And after collision, what happened? Suppose they collided and now they have become one quantity or one particle or one body as well. So, but in reality, no collision is perfectly elastic or perfectly inelastic. Okay. In reality, uh, there is neither perfectly elastic nor perfectly inelastic collisions. Okay. The what perfect, the prefix perfect is a very extreme case, extreme ideal case. Okay. That is not possible in reality. We can say it's safe to say that it is impossible in reality. So in reality, what we can have, the collision is somewhere in between them. So what we are seeing that if it is perfectly elastic, velocity of separation is equal to velocity of approach. That is one extreme case. Another extreme case is perfectly inelastic collision, where the velocity of separation is 0. So we can say that the velocity of separation will lie anywhere between 0 and velocity of approach. In reality, the value would be somewhere in between the two. So what we do, we say that uh, in reality or in practical cases, we can write that the velocity of separation, we can put a bracket, it would look nice, is equal to say some coefficient or some quantity E multiplied with velocity of approach. Okay, where such that E will lie between 0 and 1. If E is 0, what we are getting? Velocity of separation is 0, that is perfectly inelastic collision. If E is 1, then velocity of separation is equal to velocity of approach. We get perfectly elastic collision. Okay, so this quantity E is called the coefficient of restitution. Got it? And it is the reason why if you just drop a ball uh, from a height, the bounce of the ball will go on decreasing with the consecutive bounces. Okay, the height of the bounce would be decreasing, provided you just drop the ball with ball from rest. Okay, if it is a free falling case, it's not that you just deliberately you threw the ball on the ground. Definitely it will bounce higher. Even that, even then also you will see after some time the bounce height will go on decreasing and eventually it will become 0. Okay, so this important quantity is called the coefficient of restitution. So in the exam they may also ask you that define this quantity and what is its value for a perfectly elastic case or perfectly inelastic case. Okay, these kind of things you may be asked in the exam. Is it okay, everyone? Both of you, is it fine? Little time is left. We can do one thing. We are nearly to towards the end of this chapter. Tomorrow, or day after tomorrow, we may get done. Mm, one thing we can do, we can do some numerical problems. I think that would help. Like because when you are able to do the numerical problems, it means that you have understood the theory. So let us try a problem. It reads like this: that center of mass is at P, suppose, and the coordinates of P is 1, 1, 1. It's a three-dimensional case. Don't panic. You can do that. When the system of particles are of masses 2, 3, 4, and 5 kg. Now, if the center of mass now shifts to say another point Q, which is at this coordinate, on removing the 5 kg mass, what was its position? Okay, so we had a system of 4 particles of mass 2, 3, 4, and 5 kg, and the center of mass was at this position. Fine. Now they are saying that the center of mass now shifts from here to here if we remove the 5 kg mass. So what was the position of the 5 kg mass initially? Read the question and see if you can understand what it is trying to say. And if you can understand, then try this problem. Give it a try. Yes, Neha and Lachu, can you do this? Will you be able to do, or shall I help you? Position of what? Whose position? Whose position are you asking there? Yeah, it may. It's just a coordinate, huh? It may be negative. It may be less than 1. It's nothing, it's just we have to begin with the definition of the center of mass. Okay, that we know the position of the center of mass is given this by this formula. Okay. You may or you may not draw the picture, but for the sake of understanding, I am drawing it. That we have four masses. Okay, I am writing it like this. So 2, 3, 4, 5 kg. The position vectors are R1, R2, R3 respectively. And what do we mean by this thing? That is important. It means that the coordinates of this point P is 1, 1, 1. Okay. Suppose the center of mass is here at say P. What is the coordinate of P? 1, 1, 1. That means if I want to draw the vector, that is the vector joining O from P, that would be 1 I cap, 1 j cap, 1 k cap. Simply I cap plus j cap plus k cap. That is the main thing you need to understand. So here what we have initially we can say that the position vector of the center of mass was something like this. So I have four masses, isn't it? What I need to find R4, the position of 5 kg. Okay, I can put the values. Say I begin with 2 kg, so M1 is 2, it is 3, it is 4, it is 5. Here I'll be adding the masses. So 2 plus 3, 5, 5 plus 4, 9, 9 plus 5, 14. So I'll just cross multiply it. I feel you are a bit worried that, sir, how can we find R1, R2, R3, R4? Everything is unknown, isn't it? Don't worry. Sometimes we are a bit fortunate to calculate the number of unknowns, even though the number of equations are less than the number of unknowns. Those are very special and rare cases. This is one such case. So initially our center of mass was here. Now what happened? We removed this mass M4. And suppose the center of mass has now shifted somewhere here to Q. Okay. So what would be the coordinate position vector of Q now? M1 R1, M2 R2, M3 R3. And then sum, isn't it? So I won't be doing everything in details. It would be just 2 plus 3 plus 5. That would give me, 2 plus 3 plus 4. That would give me 9. I'll cross multiply it. I would be having this thing. Now I'll subtract. I'll subtract 2 from 1. Write it in an old school fashion. That is mind you that still R1, R2, R3 are unknown, also R4, and we have only two equations. So what we did in our class 9, that number of equations must be greater than equal to number of unknowns to get the solution completely. Okay, that is also true, but here we are bothered about to find only one solution, that is R4 only. So if I subtract it and see, all the terms get cancelled. So I have 14 OP minus 9 OQ, that is equals to 5 or 4. So OP I got that it would look something like this. So with that similar logic, I can say that if the coordinates of OQ is 2, 2, 2, it would be 2I cap plus 2J cap plus 2K cap. Keep 5 or 4 as it is. I think you're well aware regarding subtraction and addition of vectors. I think you know that I can only add and subtract the coefficient of I cap with that of another I cap. Okay, I cannot add this coefficient of I cap with that J cap. Component wise, I have to proceed. So 14 I cap minus 18 I cap would be how much? Minus 4 I cap. Similarly, I would get the remaining terms. So what is R4? 5 is a scalar. I can individually divide it with all the component. So I can say that therefore the position of 5 kg is, since my question was given in that coordinate style, I will write it like this. Okay. Is it clear? Neha, did you get this thing? You're asking me, is it less than 1 or something? Oh, very good. So that's a typical problem which we can come across. So that's all from my part, from my side today. If you have any question, you may ask, else we can end it. You can end the class. You can have your lunch before your GE classes. Any doubt? Okay, fine. Lachung, did you collect your ID from the college? Neha did it already. Lachung, can you hear me? Okay, fine. Okay, so I think let's end it here. Okay, thank you for attending. Let's meet again next day. Okay, so take care, both of you.